Okay, so in this video we're going to review some dynamics and momentum style problems, but we're going to start off by looking at Newton's second law. So when a force of 200 newtons exerted on an asteroid, it accelerates at 0.002 meters per second squared. Find the mass of the asteroid. Well, we can just use F equals ma, the simplified version of Newton's second law, rearrange to find mass, and then substitute the numbers in. Okay, an ice hockey player has a sudden impact force of 5,000 newtons exerted on him due to unexpected collision with the wall. The mass of the player is 100 kilograms. Find his acceleration. So we're using the simplified version of Newton's second law again, this time to find acceleration, and we get that it will be 50 meters per second squared. So compare this with the acceleration when he free falls. Well, this is about 5 times the acceleration in free fall, so we'd sometimes describe this acceleration as being 5g. Okay, so coming out of a dive, 75 kilogram astronauts in training experience an acceleration of 40 meters per second squared. Calculate the force acting on them. That's fairly simple. Could you use F equals ma? We've got 3,000 newtons. Compare this with the force that normally acts on them when they're stationary on Earth. Well, that's going to be around their weight force, so 75 times 9.81, about 740 newtons. So we're about, what's that, about 4 times bigger than the force they'd normally experience. So why is it important that they're seated and they're strapped in before they come out of a dive? Well, Newton's first law tells you that they would continue with their original motion until a force acted on them, and what we don't want is that force to be them slamming into a wall of whatever jet or plane they're in. So if you're strapped in, that is going to prevent the astronaut, I suppose we describe them, continuing with their motion. The seatbelt will make sure that they follow the motion of the rocket. Okay, so a 50-gram tennis ball may be accelerated at 1,000 meters per second squared to reach surface speed of 130 miles per hour. Calculate the force required to accelerate the ball. We're just using F equals ma, converting grams into kilograms, we get 50 newtons. Okay, so is your answer reasonable? Comment. So to me, this force seems a bit small when I think about how hard you have to hit a tennis ball, but it's definitely a force that is within the scope of a tennis player to apply. So I think it's reasonable, but for me it seems a little bit small. Okay, so an 80 kilogram skier has a force of 2,000 newtons exerted on him down the slope. Calculate his acceleration down the slope. So if we know the force, we can get the acceleration, and that turns out to be 2.5 meters per second squared. So what is the angle of the slope? Well, essentially the force that's going to be accelerating him is a component of the weight force. So we can express the acceleration on a slope using g sine theta, which we know is equal to 2.5. So we can rearrange that to find out what theta is, 15 degrees. Okay. So a force of 24 newtons acts on a mass of 6 kilograms initially at rest. Calculate A, the acceleration, B, the distance travelled prior to achieving the velocity of 20 meters per second. So we can figure out the acceleration using the simplified version of Newton's second law. Acceleration is 4, and then we know the final speed, and we know the initial speed is 0, and we know the acceleration, so we can use a Suvat equation to find out how far it has to travel, 50 meters. Okay, so a lorry of mass 3 times 10 to the 3, so 3,000 kilograms, pulls 2 trailers, each 2,000 kilograms, along a horizontal road. If the lorry is accelerating at 8 meters per second squared, calculate the net force acting on the whole combination and the tension in the 2 sets of coupling. So my diagram looks a bit like this. So first of all, let's calculate what the overall force is. Well, the total mass is going to be 7,000 kilograms times by 0.8 gives us a resultant force of 5,600 is required. So next I'm going to find the tension T1. So the back trailer has a mass of 2,000 kilograms. It is accelerating at 0.8 meters per second squared. So that allows us to calculate what the tension force is, T1. And if we want to find T2, well, T2 is acting to accelerate both of the back trailers. So that means we're going to add together their masses to give us a force of 3,200 newtons in that particular coupling. A 4 kilogram block sits on a table with a piece of light string connected to it. A force of 70 newtons is applied to the block, which just causes it to slip. What is the coefficient of friction? So because it says it's just starting to slip, we know we're on the point of slipping. So we've got this situation here, but there's going to be a frictional force opposing the 70 Newton force, and the friction force is going to be equal to 70 newtons because it's on the point of slipping. The normal contact force in this case is easy to calculate because there's only one downward force, the weight force, so the normal contact force must be equal to that. And then we can just rearrange our equation for friction to find out that mu is 1.8. The coefficient of friction between a static 3 kilogram crate and a 35-degree inclined slope is 0.3. What is the minimum force which must be applied parallel to the slope to prevent it sliding? Okay, so this is our scenario, but we're also going to have the weight force acting down the slope, and we're going to have the frictional force acting up the slope. So the first thing I do is calculate what the normal contact force is, and then from that we can calculate what the frictional force is going to be, or the maximum frictional force. So the force acting down the slope would be the component of weight force parallel to the slope. That's 3 times 9.8 times sine of 35. So we can see that the force we're going to need to apply would be the difference between the two forces we have calculated. So that needs to be 9.6 newtons to hold it in equilibrium. Okay, so moving on to momentum and impulse, but still I'm going to be drawing lots of diagrams. So a body of mass 6 kilograms moving at 8 meters per second collides with a stationary body of mass 10 kilograms and sticks to it. Find the speed of the composite body immediately after impact. So this is the scenario. We've got the 6 kilogram object traveling, and they combine together to give you an object of mass 16 kilograms. So applying conservation of momentum, or initial momentum equals final momentum, we know that the initial momentum is 48, 6 times 8. The final momentum is 16v. Then we can solve what v is, 3 meters per second. A flat truck of mass 400 kilograms is moving freely along a horizontal track at 3 meters per second. A man moving at right angles to the track jumps onto the truck, causing its speed to decrease by 0.5 meters per second. What is the mass of the, well, it says mass, but I think it's meant to say man there. Okay, so the key here is the man is not going to apply a force parallel to the velocity because he's traveling perpendicular to it. So in applying conservation of momentum in the direction that the truck is traveling, we know its initial momentum, and we know what its final mass is going to be. It's going to be 800 plus m, and we know it travels at 2.5 because it's 3 minus 0.5. So we apply conservation momentum, rearrange to find m, and we can see it's 80 kilograms, which sounds a very reasonable mass for a man to be. A kitten of mass 60 kilograms leaps at 30 degrees to the horizontal out of a toy truck of mass 1.2 kilograms, causing it to move over horizontal ground at 4 meters per second. What speed did the kitten leap? So we're initially stationary, so the initial momentum is going to be 0. Now, we don't know what the speed the kitten leaps out, but I'm only interested in its horizontal component because we know the horizontal velocity of the truck afterwards, so I'm just going to apply conservation of momentum in the horizontal direction. But we know they have to travel in opposite directions, so I'm going to give the kitten a negative velocity. So by doing that, we can solve what the horizontal component of the kitten's velocity must be, 8 meters per second, and then we can use the angle and cosine 30 to figure out what the actual speed was that they leapt out in order to have a horizontal component of 8 meters per second. So a ball of mass 6 times 10 to the minus 2 kilograms, moving at 15 meters per second, hits a wall at right angles and bounces off along the same line at 10 meters per second. What is the impulse exerted by the wall on the ball? Well, that's going to be change in momentum. So it's going 15 meters per second to the right initially, which means it's going minus 10 after the collision. So we've got a total speed change of 25, which then allows us to calculate what the impulse is. And then once we know the impulse, if we divide that by the time, that allows us to calculate what the force is going to be, and that's using Newton's second law that force is rate of a change of momentum. Okay, a hockey puck is hit across a frozen lake with an initial speed of 20 meters per second, sliding for 120 meters before coming to rest. What is the coefficient of friction between the puck and the ice? It says it's easier with energy than acceleration. So I'm going to apply conservation of energy, that the work done by friction must be equal to the change in the kinetic energy. This is going to assume the force of friction stays constant the whole time. And then in place of work done, we've got force times distance. The final velocity is 0, so that's why it's 0 minus half m, the initial speed squared. In place of friction, we can put minus mu r. And then what we can do is we can start cancelling and rearranging to calculate what u is, plug the values in, and we get that mu is 0.17, which shouldn't be too surprising. We're on ice, so we'd expect quite a small coefficient of friction. A student is trying to hold open a fire door in the school with lots of different methods to see which one works best. The automatic closing device on the door is capable of generating a torque of 100 Newton meters. The handle is 1.5 meters from the hinge of the door. The student ties a string A to the handle and connects it to the wall behind the door. The angle between the door and the string is 90 degrees. What is the tension? So this is a simple moments problem. We need the moment of the force from the tension to be equal to 100 to keep it in equilibrium. The tension is a perpendicular distance of 1.5 from the pivot, so then we can divide by 1.5 to give us what the tension is. Nice and simple. Okay, so for the second example, the force and the 1.5 distance are no longer perpendicular. So what you do here is the perpendicular distance between the tension and the pivot is now going to be 1.5 cosine 20, or we could have done sine of 70, it doesn't matter. But we still know that's equal to the torque from the closing mechanism of 100, but this time, because the distance is smaller, we need a slightly bigger tension force. The student places a fire extinguisher on the carpet in front of the door, 1.2 meters from the hinge. The coefficient of friction between the extinguisher and the carpet is 0.72. What must the mass of the extinguisher be to hold the door in place? So we're going to apply the same approach. We know the moment of the frictional force must be 100. That gives us a frictional force of 83, blah, blah, blah. And then we can apply the frictional force must be equal to mu mg, and we can then rearrange to solve for mass about 12 kilograms. Okay, so a student moves a box of books into her room by pulling a rope that is attached to the box. She pulls with a force of 80 newtons at an angle of 25 degrees above the floor. The books have a mass of 25 kilograms, including the box, and the coefficient of friction is 0.3. So if we illustrate that scenario, it looks a little bit like this. Find the frictional force between the floor and the box. Okay, so first of all, we need to calculate what the normal contact force is, which then allow us to find the maximum frictional force. So in this one, if we apply equilibrium in the vertical direction. Downwards we've got the weight force, and then upwards we have both the normal contact force and the upward component of the 80 Newton force. So if we want to find R, we're going to do the weight force minus 80 sine 25, and that's 200 and blah, blah, blah. And once we've got R, we can then calculate the maximum frictional force. It's 63 newtons, and it says that it's moving, so that means the friction would be at the maximum value. So what is the acceleration of the box? Well, we have to find out what the resultant force is horizontally. So that's 80 cosine 25 minus the force of friction. Divide that by the mass, and that would give us our acceleration. So the box is now pulled up an access ramp angled at 10 degrees to the horizontal. What is the new acceleration of the box, assuming it's being pulled at 25 degrees to the ramp? Think very carefully about this. Okay, I will. So here's the scenario now. So we've got on a 10-degree incline. So the force pulling up the slope is 80 cosine 25, same as before. The weight force pulling down the slope is going to be the weight force of the box times by sine of 10. Okay, so that's 42.58. We now need to calculate the new normal contact force, which is going to be the component of weight force that's perpendicular to the slope, so 25 times 8.81 times cosine of 10, minus 80 sine 25. So that comes out as 207, blah, blah, blah. And the maximum friction force is that times 0.3, which is 62 newtons. So the friction and the weight force together are actually going to prevent the 80 Newton force being able to pull it up the slope. And so that's actually not going to work out at all. So the acceleration is going to be 0, because that force isn't big enough anymore to pull it up the slope. A sphere of mass m moving with velocity u is involved in an elastic collision with sphere of mass 2m moving along the same line with velocity minus u. Find the velocities of the spheres immediately after impact. Okay, so this is the scenario that we have so far, and I've called their velocities v1 and v2. So we're told that it's an elastic collision, which means total kinetic energy is conserved. So then we can get this expression relating u, v1 and v2. We can also apply conservation of momentum. So here the direction of the velocity is important. So I've assumed the final velocities of the two objects will be to the right. In actual fact, at least one of them is going to need to be to the left, but it doesn't really matter. So here what I've done is I've got an expression for v1 in terms of u and v2. So I'm going to substitute that into my previous expression. So I'm going to replace v1 with minus u minus 2v2. And then that creates for us a quadratic equation with v2 and u. So what I've done is I factorised that quadratic equation, and from that we can see that either v2 equals minus mu, but that's actually impossible because that would mean the 2m mass was going back through the single mass, so that doesn't make sense. So v2 must be equal to 0.33 u, and using that we then have v1 is minus 1.7 u. So you always have to think about, we've got a quadratic, so we're going to get two solutions, but one of them isn't going to make physical sense. Okay, so we've got a uniform ladder which is 5 meters long, has a mass of 20 kilogram, leans with its upper end against a smooth vertical well. Smooth meaning it's frictionless, which is why there's no force of friction on the left hand side. The lower end is on rough ground, so there would be friction there. The bottom of the ladder is 3 meters from the wall. Draw a diagram. So this is my diagram of the situation, and this, I also spotted that this is a 3, 4, 5 triangle, so that's how I know the height is 4 meters. Okay, so that's our scenario. So calculate the frictional force between the ladder and the ground. So if we look at our diagram, there are only two horizontal forces, R1 and friction. So they must be equal to each other if it's in equilibrium. So I'm going to take moments about R2, which is going to mean the moment of the frictional force and the moment of R2 are 0. So then there are only two forces that have a moment, in one clockwise, one anti-clockwise. That allows us to solve what R1 is, the normal contact force from the wall, and we know the friction must be equal to that, so that gives us a value of friction of 74 newtons. Okay. Alright, so then final question. What is the maximum mass of a paint pot which could be hung on the 15th rung of the ladder? The gap between each rung is 25 centimeters, without the ladder slipping down the wall. The coefficient of friction between the ladder and the ground is 0.6. Okay, so the first things first, I'm going to figure out what a few unknowns are. So the first thing we can do is I'm going to resolve vertically. So I'm going to look at the forces in the vertical direction. So the only upward force is R2, the normal contact force from the ground. So that must be equal to the total weight force downwards. Now we were told earlier to use G as 10, so that's what I've done in the first stage. Once we know the normal contact force with the ground, we can work out what the maximum friction with the ground is. Because what we're going to need to do is there needs to be a force bigger than this maximum friction in order to make it slide, which is what we're looking for here. We can also figure out essentially how far up the ladder the paint pot is. So if there's a rung every 25 centimeters, 5 meters divided by 0.25 gives us a total of 20 rungs, so it's 3/4 of the way up the ladder. So what I'm going to do is I'm going to make the pivot the base of the ladder, and we're going to take moments about the base of the ladder. So the moment of R2 and the moment of friction is 0. Okay, so the 20 kilograms of the ladder, the weight force of 200 acts halfway along the ladder, so 1.5 times 200, and then the weight force of the of the M kilogram mass is going to act 3/4 of the way along the ladder, so 0.75 times 3. We know that that's got to be equal to the moment of the normal contact force from the wall, which we'd multiply by a distance of 4, because that's the perpendicular distance from R1 to the pivot. And then from this, what we can do is we can generate an expression for R1 in terms of M. So then the final stage is we know it doesn't slip if R1 is less than the maximum friction. So if it's anything up to the maximum friction, that's going to be fine. So we can put our expressions for R1 and for F max into this expression, and then we can rearrange to make M the subject, and we end up with this inequality that says that the mass has to be, in order to fulfill this condition, the mass has to be greater than minus 120 kilograms. So what this means is it will not slip if the mass is greater than minus 120. So mass has to be 0 or bigger, so mass is always bigger than minus 120 kilograms. So it will never slip regardless of the size of the mass that we actually add. You can see we could put whatever mass we want on the 15th rung of the ladder and it's never going to slip. It might end up toppling, but it's never going to slip.